Acceleration. Definition of acceleration. Future. Derivative of velocity as a function of time. Don't miss the fact that this is also velocity equals the integral of acceleration as a function of time. You need to be able to do that both as a definite and indefinite integral. Difference between the two, Gary?
What was the question?
Difference between a definite and indefinite interval.
Without the interval and with the interval. The limits.
The limits. So no, I wasn't sure what you meant by limits. Yeah, so the definite integral would have the limits, the indefinite integral would not have the limits. When you take an indefinite integral, what do you need to make sure you add after taking the integral? Michael? C. C. C is generally something you could figure out using the initial condition, the initial time being equal to 0. This, let's do these two. The derivative as a function of time, or derivative generally on a graph, loci is what? The slope. What is the integral? Back.
The area under the curve.
And the quotes?
There, it doesn't necessarily mean between the x-axis and the curve.
Between the x-axis and the curve.
There you go, Ruth.
One other little thing. Other little thing. Yes, Travis.
Below the x-axis is negative.
Below the x-axis, the area is negative. This is a classic example of that type of a question. Would be something having to do with, they give you a graph and they ask you some question about it, and basically all you have to do is figure out what the area is under the curve on the graph. We also have the equation for velocity, Winter. Derivative of position as a function of time. Again, the position then as a function of time, the velocity as a function of time, is equal to the integral of velocity as a function of time. Newton's second law. John.
Okay. The sum of the forces equals mass times acceleration with vectors on force and acceleration.
Good. That's what it was last year. What is the newer form of Newton's second law, Miller?
The ddt.
The derivative of momentum as a function of time. If the derivative of momentum as a function of time is equal to 0, what is true? Miss Yang. Conservation of, just to be specific here, the linear momentum. The sum of the initial momentums equals the sum of the final linear momentums. Whenever you sum the forces, you need to identify the direction. You need to identify the direction, and you might need to, more often in this class, you do need to identify perhaps what specifically you're summing the forces on. There might be multiple objects in the particular event, and therefore you might need to identify which objects. J is the symbol for Billy.
Impulse.
Impulse. Sometimes you might see it as an I, sometimes you might see it as a J. Both represent impulse. The equation for impulse. Sarah, Jane, Jill?
The integral of the force with respect to the time.
Good. The integral of the force with respect to time. This is also equal to Doris. I think you might have used all of your I don't knows last time.
I don't know. I'm like, oh, change in momentum.
The change in momentum.
Just kidding.
It was fine. The change in momentum. We have the impulse is also equal to the change in momentum. Not to be confused with the equation for work. What is the equation for work, please? Tyler.
Integral of force with respect to position.
The integral of force with respect to position. So please be careful to make sure you identify the difference between those two. So we could have F, actually I should put dr, it's just more general. Dr, Fr, cosine theta. All right. We have several equations having to do with energy energy and work, etc. What are the equations? Give me one of the equations and when we can use it. Sierra.
Well, you can always use the network equals the change in energy.
The net work equals the change in kinetic energy, and you are correct that this one is always true. And it is the oft overlooked one. The net work equals the change in kinetic energy. Give me another one, please, Zach. We could look at it as, we haven't done power. Sure, we could do, it's not quite what I was getting at, that's fine. Say that again, work equals? Good, because power is equal to the derivative of work with respect to time. That's true. Not where I was headed, but certainly we do know that as well. Mr. P.
Work net equals change in mechanical energy.
The work net equals the change in mechanical energy. Thank you very much.
And it can only be used when there's no friction.
When the force of friction equals 0, when there's no friction. Really? Really, I have the two written right next to one another up there. And you're gonna, I only have 4 hands up. That's it? This is sad. Red side.
That's the work due to friction and the force applied to 0.
Network equals change in kinetic energy. Network can't also equal the change in mechanical energy. It is the work due to friction equals the change in mechanical energy. This is only true when there is no force applied. One more. Having to do with energy, unfortunately no longer work. Hamza.
Is it kinetic energy initial equals kinetic energy final when there's no force applied or friction? Or is it mechanical energy initial equals mechanical energy final?
It is in fact mechanical energy initial equals mechanical energy final. The conservation of mechanical energy, yes, the force of friction and the force applied both are equal to 0. Only true when there's no force applied and no force of friction. Power, we have the equation for power. We rearrange that in terms of work as well. If you recall, this is also, work is, we have the dot product of F, the force, and the displacement. So it's the derivative of the dot product of 2. So the derivative, if you will, of force, or I'm sorry, force with the dot product of velocity. If there is a conservative force, a bell starts ringing in your head. It goes ding, ding, ding. That's right. There's an equation that's not on my equation sheet that I know is always true when there's a conservative force. Ding, ding, ding. That equation is Miller.
F sub x equals negative du dx.
This is the potential energy associated with a particular force. Whenever you have a conservative force, this is always true, and again, it is not on your equation sheet. Please remember that equation. We have 2 different equations for the center of mass. One is for the center of mass with a bunch of particles. Center of mass with a bunch of particles. Eric, there's only one today.
Oh, it's like position 1 plus position 2 plus position 3 over mass 1, mass 2, mass 3. Like with the dot. I don't know if that's right now.
I do. Do you?
It's position 1 times mass 1.
Okay, got to include the mass. The mass affects where it is located, or where the center of mass is going to be located. So the position 1 times mass 1 plus position 2 times mass 2 plus however many we have. Let's see. That is one. That's for a bunch of particles. We could have, oh, and you could do the y, you could do x, you could do z. We could also put r just as a general. So let's talk about the r, center of mass. This is for an object that has shape. Motate. The center of mass for something that has shape.
Is it IW squared?
It is not I omega squared. The center of mass of something with shape. Tyler.
1 over the total mass times the integral of du
dm over r. Close. Okay.
RDM.
Just r times
Time.
dm. Very cool. Let's see. So we have, of course, have the three different types of mass density. I won't walk through them. They're the same as the types of charge density we had last time: linear, surface, and volumetric mass density. We have, let's see, three different equations. I have a lowercase cursive s. Lowercase cursive s stands for Miller.
Arc length.
Arc length. Arc length is equal to 2. Tim? R times theta. If I take the derivative of this equation with respect to time, I get what equation, baby? I get what equation?
ds.
ds dt, true.
This equals.
Okay, well, I'll write that up. ds d over dt is equal to r times d theta dt. I agree with that. What's the derivative of the arc length as a function of time? Sierra?
The tangential velocity.
This is the tangential velocity. Is equal to r times the derivative of angular position as a function of time. Sierra?
Which is angular velocity.
Angular velocity. Okay. So if I take the derivative of the tangential velocity equal to the radius times the angular velocity, what equation do I get? Look.
You said it again.
I took the derivative of the arc length. I'm now going to take the derivative of the tangential velocity equation. What do I get?
The acceleration.
Not centripetal.
Oh, tangential.
This tangential acceleration is equal to
The radius times alpha.
the angular acceleration. The derivative of the angular velocity is going to, with respect to time, is going to be the angular acceleration. All right, that brings us to centripetal acceleration. Two different equations for centripetal acceleration. John, give me both.
T squared over vt squared over r.
Vt squared over r, the tangential velocity squared divided by the radius, yes?
And r omega squared.
The radius times the angular velocity squared. That brings us, of course, to if we have something moving in a circle, we can sum the forces in the direction. That's equal to mass times the centripetal acceleration. To all of that. Torque. The equation for torque should be r cross f. The r, the lever arm cross product with whatever force we're talking about. Please recall that we need to be able to do this in two different ways. You need to be able to do the matrixing I, J, K with Rx, Ry, Rz, and Fx, Fy, and Fz. You have to be able to do it that way. It is also equal to Rf sine theta if we're not dealing with unit vectors. The net torque is equal to net torque. Nitish.
The moment of inertia times the angular acceleration.
Great. I times alpha, the moment of inertia, times the angular acceleration. Let's see. When you sum the torques, you need to identify, Sarah Jane Joe?
The axis of rotation.
The axis of rotation. Please make sure you identify the axis of rotation, which brings us to I, the moment of inertia. What is the moment of inertia? I'm not looking for an equation, but rather, what is it? Catherine.
It's rotational.
Rotational mass is a good way to look at it. So what does it mean that it's rotational mass? Travis?
It's like how much it resists change in rotation.
True. How much it resists a change in rotation. So how much it resists what? I agree with that, but what specifically? Angular acceleration, just to put it into physics terms there. So remember, the moment of inertia is otherwise known as rotational mass, or the measure of the amount of resistance to an angular acceleration. Good. We have two different equations for the moment of inertia. One is for particles, one is for an object with shape. Bailey, give me one or the other. Moment of inertia.
Moment of inertia is the integral of r squared
r squared dm. So notice, these two often get confused. They're both with respect to mass. One has r, one has r squared. One does not have the mass total. So be careful of that. This is clearly for an object with shape. What about the moment of inertia for a series of particles, please?
The integral of r squared. Sum of mr squared.
The sum of mr squared, where however many we have from I to however many we have. I guess that's infinity is not a good thing to do. That would be for this one. So it is simply we take however many we have and do mr squared, the addition of all of those. It's on all of those. Oh, so what happens if the net torque? We have another equation for net torque. What's the other equation we have for net torque? Renza. dl dt, and L stands for? Angular momentum. What if that is equal to 0? If the derivative of the angular momentum as a function of time is equal to 0, Mr. Peter?
Is not rotating.
Not necessarily.
Oh, it is not angularly accelerated.
What I'm getting at more is this is the fact that the derivative of the angular momentum is equal to 0. The derivative of the angular momentum as a function of time, Eric, means, if that's equal to 0,
Angular momentum conserved.
that means that the sum of the initial angular momentums equals the sum of the final angular momentums. Please remember, you have to identify an axis of rotation when you're talking about conservation of angular momentum, bless you, because it comes from the fact that the net torque, the derivative of the angular momentum as a function of time, is equal to 0. Therefore, you need an axis of rotation. Please do not forget that. We have a couple of, let's see, definitions here. We need a couple of definitions for angular momentum. Give me one, please.
Definitions like
Miller, help him out. He's not seeing.
r cross p.
R cross P, or RMV sine theta. This would be for, Tyler?
Wait, what?
This would be for what type of object? I don't know. That's okay. Dorfstetter's going to help us out. See, we're running out of I don't knows. I should put them in a bag. We have a set number. Sarah Jane?
I'm trying to, what does that say?
R cross P or M, there are two M's there. RMV sine theta. I apologize. So what is this? Unfortunately, my board is mostly black at the moment, so it's getting harder to read, but it's okay. Someday it will be clean. So this is the angular momentum for what, Renza?
Like
One particle. This is for a particle. We also have the angular momentum for an object, a rigid object with shape. Loki, what's the equation for that? That's okay. Dorfstetter? I omega. The moment of inertia times the angular velocity of an object with shape. Let's see. Oh, getting back to conservation of the angular momentum, please recall that one of the things that we had to do often for when we had like an object, here was our axis of rotation right here, here was theta, this was r. The issue was with the angular momentum being equal to rm, that's what happened, being equal to rmv sine theta. As the object is moving closer, r is changing, theta is changing. So we have an issue. What is the solution to that problem? Both the r and the theta are changing. Eric?
Take like sine theta. It's like r. The little r and sine theta are replaced by r. So
Okay. The opposite I'll label right here as y divided by the hypotenuse, which is r. In other words, y is equal to r times the sine of theta. And y is a constant, even though r and theta are both changing. the value r sine theta is not. Please remember that basic concept. Let's see, we have the rotational kinetic energy. Rotational kinetic energy, please, Travis, equation.
1/2 I omega squared.
1/2 I omega squared. Notice, just like 1/2 mass times velocity squared, we have rotational mass and rotational velocity right there. Rolling without slipping. Bless you. In rolling without slipping, generally we have a conservation of energy, but we have both translational and rotational kinetic energy because it is both moving linearly and rotating. And the velocity of the center of mass of the object is equal to r times the angular velocity of the object about its center of mass. Kepler's third law. Kepler's third law had to do with planetary objects. Basically, you're talking about an object in orbit around another one. And if you recall, we simply draw a free body diagram, sum of the forces in the in direction is equal to the force of gravity, which equals mass times the centrifugal acceleration. Big G, the mass of one object, the mass of the other object, divided by r, the distance between the two of them, squared, is equal to the mass times the, and there are different ways to do it. I'll do the mr omega squared, where omega equals the change in theta over change in time, or 2 pi divided by the period. Basically, that's it for Kepler's third law. Who knows exactly what you're going to be solving for? You might be solving for the period, but we can substitute stuff in. That's the basic idea behind Kepler's law. I pointed out that you should not memorize it. Basically, you just need to know how to derive it using that. Universal gravitational potential energy. The equation for universal gravitational potential energy, please. Yuchik.
Negative d at point.
Please don't miss the negative. It is an important one. Where is the 0 line for universal gravitational potential energy? Rensak. Remember, the 0 line is preset. It is that r is equal to approximately infinitely far away. And if that is true, that means that the gravitational potential energy is equal to 0, which makes sense if you look at it. Simple harmonic motion. The equation that defines simple harmonic motion, if you can show that the equations boil down to this, you know the object is in simple harmonic motion. Nick.
D squared x over dt squared equals negative omega squared x.
Bless you. The second derivative of position or acceleration as a function of time is equal to the negative of the square of the angular frequency times x. If you could show something boils down to that, then you have shown that it's in simple harmonic motion. We should have memorized several angular frequencies for different simple harmonic motions. Give me one, please, Gary. Dorstead included that. Can you believe he asked me that? He said that. All right, we'll go with this. Dorstead, what am I asking?
For like different angular frequencies.
Of, for example, what?
Like a spring or
A
something?
mass spring system, for example. What else, Travis? There are 3 examples: a mass spring system, a pendulum, good, yes, and the last one, which doesn't have to do with mechanics, but I'm going to bring it up anyway. Loki. LC circuit. You should have all 3 of these memorized, the angular frequency for all 3, and you should be able to derive them. Please give me the angular frequency for one of them. Gary.
Like a
Red side.
Oh, that's time constant.
Yeah, that's I'm sorry. Hold up.
1/√LC.
1 over the square root of L times C, that is for an LC circuit. We also have the angular frequency for either a pendulum or a mass spring system. Miss Yang?
M over square root of M over K.
The square root of M over K, this is for
It's mass.
a mass spring system. And one more. Miller?
The last one was K over M.
It is, in fact, K over M. Now, you should be aware that on your equation sheet you have the equations for the periods of these various things, so you can't actually get it from your equation sheet. That's not helpful for multiple choice, but it is helpful nonetheless. And the last one, the angular frequency for a pendulum. You could also figure it out from dimensions as well. Yes, Travis?
Square root of G over L.
Square root of G over L. Again, you could look at this, because this is in meters per second squared divided by meters, so it would give you 1 over second squared. The square root of that would be 1 over seconds or radians per second, so clearly that is correct. We have the equation for the position as a function of time of something moving in simple harmonic motion. What is that equation?
The amplitude times the cosine of omega t plus
The thing.
the initial angular displacement.
We'll call it phi,
Okay.
the phase constant, but yes. And you can take the derivative of that to figure out the velocity as a function of time, so on and so forth. We also have the energy of a mass spring system, for example, would be equal to 1/2 k x squared plus 1/2 m v squared at its maximum displacement from equilibrium position, which is called what class? The amplitude. The energy would be all as a function, all in the elastic potential energy, because the velocity would be equal to 0 at the location where we have the maximum velocity. The x, the displacement from the equilibrium position, would be equal to 0, and therefore it would have its maximum energy there as well. That is my brief review of mechanics.